This training will explain NUCAPS and Gridded NUCAPS and how you can use them in the forecast process. I'm Scott Lindstrom from SIMS. NUCAPS is an acronym that now stands for NOAA-Unique Combined Atmospheric Processing System. It was first known as the NOAA-Unique CRIS ATMS processing system when only data from SUMI NPP were used. So it used the CRIS and the ATMS. But then infrared and microwave data from MEDOP were incorporated into the NUCAPS algorithms, so the acronym was changed. The NUCAPS data that you see on AWIPS coming via the SBN are from NOAA-20. You can also get SUMI NPP NUCAPS from a direct broadcast such as the one at GINA in Fairbanks. If you have 2 satellites, you get twice as much data. One of the first challenges with using these data is where are the orbits. And you can find the orbit paths online, choose the Arctic projection, and then choose NOAA-20 or NPP. And you'll see something like this. Orbits are similar for both NOAA-20 and SUMI NPP. These are the orbits from January 25th, 2020. They're similar from day to day. The morning orbit, which descends from the pole toward the equator, starts somewhere just north of Greenland and then moves southward over Alaska or regions nearby. Here we have something for March 27th, and you see the same kind of thing. Morning orbits are descending, emerging from somewhere near Greenland and then spreading southward over Alaska. The afternoon orbits are ascending, and they converge toward a point north of Eurasia. If you compare passes from one day to the next, they're fairly similar. So here we have something from March 27th. Here's March 31st. There's a cluster of morning passes and a cluster of afternoon passes. Every 16 days, there's an exact repeat. The C in NUCAPS is combined. What is combined? On SUMI NPP and NOAA-20, infrared data from the CRIS, the cross-track infrared sounder, is combined with microwave information from the ATMS, the Advanced Technology Microwave Sounder. Data from NOAA-20 are downlinked at both Svalbard and McMurdo, and then that data flows through a variety of computers so that it shows up at the WFO in about 60 minutes. Alternatively, if you have access to a direct broadcast antenna, such as at GINA in Fairbanks, you can have a quicker data flow where the data will show up in about 30 minutes. Data are available where upper air soundings are not taken, and they occur over Alaska at about the same time as the upper air soundings, so you can do comparisons between the NUCAPS profiles and the few upper air stations that are in Alaska to convince yourself that they're showing you similar features in the atmosphere. Data shows up about 60 minutes after it's observed for NOAA-20. This is a big improvement over the SBN feed for SUMI NPP. Why might you want to use these data? Well, if you're looking at a model forecast to try to determine what the thermodynamic structure of the atmosphere is, you might have a model that's giving you a bad forecast. That's shown here on the right-hand side from the HRRR. In reality, that deep convection has not developed yet. You want something more grounded in reality, like the observations from satellite. The profiles are created with a 2-step process. The regression uses static coefficients from 4 focus days, 1 in each season, to create a first guess or a cloud clearing field. So this gives the best statistical fit to the data. It uses all the sounder and microwave channels. Subsequently, a retrieval is used that minimizes an observation minus calculation value. This is an iterative procedure, and if it converges to a solution, you get a sounding. If it doesn't converge to a solution, you still get a sounding, but it's flagged. The retrieval doesn't use all the channels, it uses a subset of them. The retrieval is using a radiative transfer model with 100 standard levels. So if you look in AWIPS, you will see 100 levels from these profiles. That's a lot more vertical levels than are warranted by the sounder resolution. In fact, the vertical resolution is shown here. So in the troposphere, you have about 6 to 10 layers of temperature and about 4 to 6 layers of water vapor information. Don't go into a NUCAPS profile expecting to see a lot of vertical variability. One of the reasons for that is that the profile is actually over a fairly large region. It's sampling a volume. The retrieval does not use all of the CRIS channels. It uses 399 out of 1,305. 24 different ones are used for surface temperature, that's shown in green. 87 are used for atmospheric temperature. 62 are used for water vapor. The channels are chosen for wavelengths that are sensitive to only one gas. For example, you wouldn't choose a wavelength in the retrieval that is sensitive to both water vapor and to sulfur dioxide. You would choose a channel that's sensitive only to water vapor or only to sulfur dioxide. All of the ATMS channels, all 22 of them, are used in the retrieval, however. The biggest problem for satellite-based soundings is clouds, and the biggest problem for NUCAPS is uniform clouds. As we can see down here on the right, NUCAPS can do a cloud retrieval in between clouds, but if you have a uniform cloud field like you have on the left, you will not be able to get a retrieval. Each ATMS footprint includes 9 CRIS fields of regard, so 9 CRIS infrared channels are overlain by one ATMS footprint. When the satellite is looking straight down, those 9 fields of regard are fairly tightly packed together and they're circular. There are 30 fields of regard in one scan line for CRIS. At the edges, the fields of regard become a little bit more elliptical and they're much more spread out. Each of the collection of 9 fields of regard shows up as a single dot in the NUCAPS sounding availability plot, where that dot is the center of the 9 fields of regard. If you click on NUCAPS sounding availability, you'll see something that looks like this, where we have a swath of points. The green points are where the retrievals, both infrared and microwave, have completed successfully. The yellow dots show where the infrared retrieval failed, and the red dots show where the infrared and microwave retrievals have failed. NUCAPS data are underneath the Satellite tab in your AWIPS. Underneath Satellite tab, you'll see a second tab for SUMI, NPP, and NOAA-20, and underneath that you'll see NUCAPS sounding availability and gridded NUCAPS. If you click on NUCAPS sounding availability, you'll see a plot that looks like this on the right. Green dots mean that both infrared and microwave retrievals have successfully completed. Yellow dots are regions, typically where it's cloudy, where the infrared retrieval has failed, but the microwave retrieval has completed successfully. Red dots, typically where it's precipitating, are where both infrared and microwave retrievals have failed. On the right-hand side is what you'd see with AWIPS. On the left-hand side is the actual orbit for NOAA-20 at this particular time. And you'll note that the timestamp in AWIPS is actually before the time of the observation over Alaska. 90 minutes later, a second pass came over Alaska. Then there was another one 90 minutes after that, and one 90 minutes after that. 4 different passes in each cluster of passes. There are 4 in the morning, 4 in the afternoon that are giving you data in and around Alaska. Morning passes or descending passes, again the timestamp is after the time of the observation. So here we have the one that's around 10Z, 90 minutes later, around 12Z, then another 90 minutes, and another 90 minutes after that. That's a lot of data to look through individually. Pop-ups QTs will streamline that process. So in the volume browser, choose Pop-ups QT. Then you right-click anywhere in the image and you choose NUCAPS soundings for what you're going to be sampling, and you turn on sampling. And then when you mouse over each individual point, that sounding will show up in the Pop-ups QT window. If you're looking for a temperature threshold, this is a nice way to find it, or if you're looking for boundaries. If you're looking for changes in stability over a region, Pop-ups QTs are an efficient way to do that, because you can scan through many soundings fairly quickly. It's much more efficient than laboriously clicking on each sounding. NUCAPS soundings have been demonstrated at the Hazardous Weather Testbed at the Storm Prediction Center for about 4 or 5 years now. The focus there is on convective weather, and the forecasters have found the product very useful. One of the things you might note when you look at NUCAPS soundings is that the boundary layer temperature and dew point might not be representative of what you see going on at the surface based on nearby observations. So in this particular example, we're going to look at the sounding near Jacksonville, and you notice what the temperature and the dew point there are, 73 and 60. If the sounding from NUCAPS is different, there are ways to modify the NUCAPS sounding within AWIPS. So ask yourself, do surface values match the observations in the nearby METAR, which, as you recall, was 73 and 60? In this case, not really. There are a couple of ways you can edit. You can click on Edit Data, and that brings up a window where you can edit each of the 100 levels that are in the NUCAPS plot in AWIPS. That's more levels than are warranted by the vertical resolution of the sounder information. Choose a selected level, and then enter the values you think should be in there, and then you click Apply and Close. Alternatively, you can toggle Edit Graph from off to on, and draggable points show up. And you can move those points to values you think are appropriate. So in this example, I'm going to first change the surface values, and then I'll change the values right above the surface. And then I toggle Edit Graph back to off to save those choices. I can also click Reset if I decide I've made an error. But once you toggle the Edit Graph to off, you'll have a new sounding. And comparing the modified one on the left to the original on the right, you'll notice some of the convective parameters have changed. In this case, the level of free convection is a little bit different, the LCL is a little bit different, and the thermodynamic variables will change as well in the readout. This is the first classic example of how to use NUCAPS, and it came from Dan Neatfeld, who was then the SU in Omaha. This was a case where the GFS was predicting precipitation, and in the afternoon, when NUCAPS would be overflying, there's a broken cumulus field, and the question was, is that cumulus field going to develop sufficiently that precipitation as called for by the GFS is going to fall? If you had looked at a NUCAPS profile from that day, you would have seen something like this. The temperature and the dew point fairly well matched what was going on with METARs, so there wasn't a burning need to adjust the lower part of this particular NUCAPS profile. The CAPE was about 50 joules per kilogram. The sounding was fairly dry. You would not necessarily expect shower development in this kind of air mass, and nothing happened. But a couple of days later, there was a high-risk event over Omaha, and again, we're going to look at some NUCAPS profiles from that day. First, we'll look at the sounding in that green, that's boxed in green, that's just south of the Omaha forecast office. Before I click on it, I want to draw your attention to the dew point gradient that's shown in this plot with mid-50s to around 60 in the northern part, dew points closer to mid-60s pushing 70 in the southeast part of the plot. So what does that sounding look like? Here it is, and this one has been modified so that the surface observations in the profile match nearby METARs, that is a temperature of 83 and a dew point of 63, and this gave a surface base CAPE of around 1900, so fairly healthy. We looked at the sounding that's in the green box. Now we're going to look at the one just to the south, and that sounding is in an air mass that has more moisture in it. So look at the difference in the surface dew points, upper 50s to around 60 near the forecast office OAX, but in the region of the red circled NUCAPS to the south, dew points are closer to 70. Here's what the unmodified sounding looks like there. The temperatures near that sounding were in the mid-80s, and the dew points were around 70, and those are not reflected well in this particular sounding. It still has a surface base CAPE exceeding 600. But if we adjust the sounding so that the surface-based properties are more in line with what you see in the observations, the surface-based CAPE is around 3100. So there is a significant north to south instability gradient that's very well captured by the NUCAPS profiles, and that's going to help inform your decision making on this particular day. In 2019 and 2020, something new has been added to AWIPS, and that is gridded NUCAPS. The thermodynamic information in the individual profiles has been put on a horizontal grid. You can get a better idea of how the thermodynamics are varying in the horizontal by these gridded fields. So it's new to the SBN. It's not necessarily new to Alaska because these gridded NUCAPS fields were given a test run, so to speak, in Alaska over the past couple years. You can find some of the gridded NUCAPS underneath the satellite tab, right underneath NUCAPS sounding availability. If you go into the product browser, you'll see many more fields that are available. This is all thermodynamic information. Here we have an example with NUCAPS from 1139 on March 31st. The gridded NUCAPS have slightly different times. If you're time matching, this can cause some issues, so that's just something to keep in mind. Each individual NUCAPS swath might have multiple gridded NUCAPS fields that have slightly different times. Here's an example from CONUS showing gridded temperature fields associated with a precipitation event, a snowfall event, over the southern mid-Atlantic states, North and South Carolina, where the gridded field is the binary probability of temperatures less than 0 at 950 millibars. There are many different thermodynamic variables that you can look at. You can look at individual temperature layers as well, temperature at 850, 900, and 950. You might use this to help you determine where the rain snow line is. In this particular example, I've changed the enhancement that's used so that 0 Celsius is in black. Put this in a procedure so you can see where the gridded NUCAPS suggest where the rain-snow transition line might be. Over Alaska, you have multiple passes, so you have fields that are 90 minutes apart that overlay pretty nicely. So we're looking on the north slope here, and you'll see that fields aren't moving very quickly, so there is a nice temperature gradient here. This is looking at a layer value between 850 and 700 millibars. You could look at 850, you could look at 700, you can look at the layer values, and you can see how things are changing with time over 90 minutes. This is another example over CONUS where we have the total totals indices. Values exceeding 50 are just to the south and west of a convective complex that just before this NOAA 20 pass was putting down a tornado in Nashville. So it captures the instability that can be feeding into the convective system. Here's another example showing the lapse rate from 900 millibars to 700 millibars. We have a region with small values, so a very stable region. If we look at the night fog brightness temperature difference indicating stratus in that region, maybe you can use that lapse rate to diagnose the strength of the inversion. That might give you information on how long it might take for that stratus to burn off. What might you use NUCAPS for? There are lots of different examples here. One thing I don't show that is included in the gridded NUCAPS is the Haynes index. That's useful for fires. Here are some useful links that you can get more information and a summary of what I've just talked about. This concludes the short training on NUCAPS and gridded NUCAPS. Thanks for listening.